All right, everybody's in a good mood now, so we'll go ahead and get started. Thanks for everyone for coming out. This will be session 4 of the workshops where we're looking at the meteorology behind tornado forecasting, and in this case, we're going to talk about the conceptual models to describe supercells and tornadoes. So this is essentially the linchpin of, why do we try to forecast tornadoes and supercells the way we do? It's based on the conceptual models we'll develop this evening. All right, just the reminder where we are in the sequence. This is session 4, and we're following the discussions on severe storm ingredients, lapse rates, moisture, sources for lift, and vertical shear. So we're going to use that information to build the conceptual models here, and then that sets the foundation for the rest of the course. All right, we talk about supercells. Most people here are probably familiar with supercells. These are rotating, persistent, reproducible storms. They essentially reproduce themselves. The characteristic feature would be the mesocyclone. You can see here the lowering, striated cloud base, and updraft sides. This is pretty typical structure, especially out in the Great Plains. These storms are responsible for a vast majority of significant tornadoes, very large hail reports. They're generally the most damaging thunderstorms that you encounter, so it's very important that we know how to forecast these events with some accuracy and reliability. So what we want to do is say, what makes a supercell thunderstorm tick? And we'll use that information to try to develop a forecast strategy for them. Okay, so what makes a supercell? I mean, this is the crux of the matter is what does it take to get a supercell thunderstorm? Well, we talked about deep convection before, and in this case, the energy source for the updraft is CAPE. So it's convective available potential energy. It's the energy released through the latent heat of condensation. So we condense water vapor, we release heat. That ends up being the source for the thunderstorm updraft. Okay, so we know CAPE is involved. We have to have some measure of buoyancy. We also need vertical wind shear. That's the difference with just background convection is we're talking about a rotating storm, a persistent rotating storm. So where does that rotation come from? And it doesn't just happen magically. So we have to come up with a description, a physical description based on the storm environment for the source of the rotation. Now, we talked about hodographs. This was in the session where we were looking at vertical shear and lift. Here, we're going to focus on the straight hodograph first, which would be the kind of a specialized case with the splitting supercell storms. And the importance is the curvature and the length of the hodograph. That's a way, if you recall from, again, session 3, we were talking about the hodograph itself. The length of the hodograph is a measure of vertical shear directly. So you're talking about connecting the endpoints of all the wind vectors starting from the origin going up in the atmosphere. So the difference between those two is a shear vector. So the hodograph itself is a series of small shear vectors. So it's a measure of vertical shear. A long hodograph is more favorable for rotating or long-lived storms, and a curved hodograph, especially in the low levels, is more favorable for a rotating storm. Now, we'll talk about the signs of the curvature and that sort of stuff coming up. And then, of course, we have to get the right kind of storms to start with. If you have the wrong sort of background forcing for ascent, now we haven't talked about it at this point, but we'll look at convective mode coming up soon in 2 sessions. And the point is we have to start as discrete storms, and you have to have a background environment that favors maintaining discrete storms. So it's not quite as simple as just saying, do we have enough vertical shear to support supercells? It's can we maintain a discrete or cluster mode of convection if you want long-lived supercells. All right, mid-level rotation. So the question is, what's the importance of mid-level rotation? Because that's the unique feature of a supercell thunderstorm. It's a rotating updraft. What is it about a rotating updraft that's important? And so the question is, I know some of you, maybe a lot of you, have discussed some of these things in coursework. Anytime you have rotation in this regard, you have a pressure perturbation. So we're talking about where you have strong rotation in the mid-troposphere associated with the updraft. You also have a strong pressure perturbation. That's going to try to rearrange mass. If you essentially create a strong mid-level low, you're drawing in air from below. That's part of the mechanism for how the supercell recreates itself and sets the stage for propagation. So it's that pressure perturbation associated with the fact that the updraft is rotating. So where do we get that from? Again, this is a function of the vertical shear and the buoyancy. And what's more important about the pressure perturbation is where the response to the perturbation is strongest is below the perturbation in the vertical. So that's where it's drawing air in from below. which means you have an updraft in the low levels that's substantially stronger than it would be based on buoyancy alone. And that becomes important when you talk about overcoming convective inhibition, or the storm recreating itself into a new area. So essentially, this pressure perturbation is what is driving new updraft development and that familiar off the hodograph or rightward propagation for a typical cyclonically rotating supercell in the northern hemisphere. All right, another kind of secondary thing, we're not going to get into any detail here, but the idea of rotating updraft is more resistant to decay. It's just more of a turbulence argument. It's just a more stable configuration. So it tends to, and if anyone's ever seen some of these storms go into high inhibition environments in the evening from chasing, I mean, they'll go down to where there's just the last shred of an updraft. As long as it's rotating strongly, it will still try to continually initiate new updrafts with the pressure perturbation until the whole process just ceases almost instantaneously. But the familiar chicken neck, if someone's seen that, where you watch a supercell updraft shrink down to where it looks like it's literally feet across at the end, and then poof, that's the last updraft pulse, and you're done. The only reason you get to see that is because of the influence of the pressure perturbation. All right, here's may or may not be a familiar animation of tilting of horizontal vorticity by an updraft. This is a special case of the straight hodograph. So what we're doing is we get the picture on the left of just the vorticity. This is in the case of a storm where it may or may not be streamwise already, but if we start with the crosswise case. Now when I say crosswise, we're talking about a straight hodograph. So we'll go back to the right-hand rule, and we're going to talk about this in a little bit more detail in the next couple of slides, but hopefully most of you are familiar with the right-hand rule. The idea is you point your fingers, you curl them in the direction of the shear vectors, your thumb points in the direction of the vorticity vector, your thumb on your right hand. So we can, from this case, we have something that could be akin to easterly low-level winds veering around rapidly to westerly. So the winds are all east-west, they're calm somewhere in the lower middle part of the profile, and then they're westerly aloft. That's going to give you a straight hodograph, which on the hodograph plot, it would just be a straight east-west line across the diagram. The right-hand rule says curl your fingers in the direction of the shear vectors, which the hodograph up would be to the east or to the right on a typical hodograph. Your thumb's going to point to the upward or to the north is what that would be. So what this illustrates is you can consider this a case where the winds veer rapidly from easterly in the low levels to westerly aloft. The vorticity vector is oriented to the north. So this would be the horizontal vorticity that's the result of the vertical wind shear. This is the source for the rotation in the updraft. Now, do you notice anything about this particular animation? Is the updraft itself, the core of the updraft, rotating at this point? No. I hear no. Any guesses as to, so where is it rotating? So we hear the notion that it's rotating on the flank. So what we're doing in this case, this is what we mean by crosswise vorticity. We're rearranging this vortex tube, which is an illustration of the horizontal vorticity, but it's only on the edges of the updraft. So what we're doing is we're creating cyclonic and anticyclonic rotation, cyclonic in this case on the south side of this new updraft and anticyclonic on the north side, but it's not co-located with the updraft itself. Do we have a supercell thunderstorm at this point? No, we do not, because we don't have the correlation between, or essentially the updraft is not itself rotating. We've just essentially rearranged horizontal vorticity, but we have created weak pressure perturbations. We have reoriented the vorticity vector from horizontal to vertical, so we have weak cyclonic rotation on the south flank of this updraft, weak anticyclonic rotation on the north flank. Again, you create rotation like this, there's a pressure perturbation. This is on such a short time scale that it's actually, they both act as lows. So anticyclonic or cyclonic doesn't matter. They're both pressure mins associated with not strong rotation in the mid-troposphere, but at least a maximum in rotation, where you have reoriented it most into the vertical. Okay, so this is just my cartoonish version of that situation before. Now we're just looking at, again, think of this as, and pretty intuitively I labeled the ground. So the brown stuff is the dirt there. We've got easterly winds in the low levels, quickly changes to westerly aloft. Right-hand rule, curl your fingers in the direction of the shear vectors. Your thumb points into the page, which would be your horizontal vorticity vector. Okay, so now we're we've flipped our frame of reference. We're looking down from above now. So this is that updraft. Instead of looking at it a side view, we're looking from above. South would be down, north would be up. And we're looking at those pressure perturbations that we've created due to the tilting of the horizontal vorticity vectors. So we've taken that vortex tube and we've oriented it in the upward on the south side and downward on the north side of the updraft. I mentioned that you've got weak rotation associated with those vortex tubes. We haven't really amplified it yet, but we do have a weak pressure perturbation. Now, at this point, again, my pretty storm here, it's just moving with the mean wind. So there's no propagation, nothing interesting going on just yet. We go to the next step. What do those pressure perturbations do? If we've got a low in the mid-troposphere, what's it going to try to do? Just like you see with a surface low, it's drawing air in horizontally to the cyclone. In this case, it's trying to draw air in from below into the pressure perturbation. So there's a low, and it's not really a vacuum, but it's the idea that there is a tendency for mass flux upward into the pressure mid. If you have sufficient buoyancy and sufficiently weak convective inhibition and sufficient moisture, this weak pressure perturbation can indeed initiate new updrafts. The trick now is, where are these updrafts with respect to the horizontal vorticity tubes compared to earlier? If you look at it now, you're initiating them in a different direction than you were moving with the mean wind, which was necessarily on the hodograph. So what we've done is we've created a case where the vorticity is becoming streamwise. Instead of being on the flanks of the updraft, it's actually ingested directly into the updraft, and this is a function of it propagating off the hodograph. So we've got the storm moving in a different direction, or now we've got essentially two storms. So we're creating two new ones. They're moving in sort of mirror images, propagating to the right or south of the hodograph and north of the hodograph. One would now be rotating cyclonically on the south side, anticyclonically on the north side. And again, so we're creating a new updraft. Now we've got streamwise vorticity, because for this new storm motion to the east-northeast and the east-southeast, a component of that vorticity is directly streamwise, which means the updraft itself is rotating from the get-go. So now we can actually have something that we call a positive feedback. It's actually now drawing in the horizontal vorticity directly. The updraft itself is rotating. And what's the important thing about that? Why would it matter that the vorticity be streamwise? Any guesses as to why that would be important? It's not the streamwise part. The key is the link to the updraft itself. So if you think about that, what is it about the updraft? Well, it's got the pressure perturbation, but what is the key thing that a thunderstorm updraft is going to do to the vorticity? Think of the vorticity equation, the stretching term. You have rapid vertical accelerations associated with a thunderstorm updraft. Now you have strong vertical stretching, so you rapidly amplify that horizontal vorticity. You can do this by a couple of orders of magnitude. So you take this very diffuse background environmental rotation about a horizontal axis, reorient it into the vertical, amplify it a great deal, and you get the familiar mid-level mesocyclone, which can actually have very strong vorticity associated with it. So again, these background changes from 10 to the minus 4 or 10 to the minus 5, looking at vorticity, to like 10 to the minus 2. So these are huge increases in vorticity, and it's due to the stretching associated with the updraft. So that's the important thing, why you don't want the vorticity just solely on the flanks of the updraft. You don't maximize the stretching term. That's tilting. Stretching has to be involved with the updraft. Okay, so the straight hodograph case, the background vertical shear provides the vortex tubes, but they're oriented crosswise. You get initial rotation on the flanks of the updraft, and then those initiate new updrafts on the flanks, and those new updrafts become more streamwise in the description, and that's the familiar propagation, both left and right off the hodograph. And again, that net result would be streamwise vorticity, and you end up with a stronger, longer-lived rotating updraft, both cyclonic and anticyclonic. So that's the mirror image storm split case. Okay, we'll show an example of one, which isn't necessarily a familiar one. This will be an elevated left-moving thunderstorm. You see the storm split. It doesn't have to be surface-based, so you can see the same process operating with elevated convection. This is one where the most unstable parcel is based around 850 millibars. You can see an effective inflow layer which is just that layer. And we'll talk about this some more here coming up. It's the idea that the layer potentially feeding the updraft is, again, rooted above the surface. Now, if we go and look at the hodograph for this case, that inflow layer is denoted by those two blue lines. So the bottom line would be essentially the base of the inflow layer, which is near 1 kilometer above the ground. How would you characterize that hodograph? From about 1 kilometer, somewhere near the x-axis where it crosses at about 10 or 20 knots. What, is that a curved hodograph, straight hodograph? How would you characterize that one, by and large? Pretty straight hodograph. If there is any curvature in the upper part, so again, these, if you've noticed, you'd see this in Sharpie or you'd see it with the SPC in sharp soundings. The red section is the lowest 3 kilometers, so the upper part of that, how would you characterize the curvature in the upper part of that? If you look close, you can see 1 kilometer is just to the right of the y-axis on there. So all the little loop, the clockwise loop in that hodograph is all down below 1 kilometer. So what about above that? It's straight. If there's any curvature, how would you characterize it? Clockwise or counterclockwise? If there's any. And it's not a trick question, so. It's actually counterclockwise. If you look closely, again from about 1, look at the curvature, the inflection, it actually bends down toward the lower left. So that's actually the type of curvature that would favor anticyclonic rotation in a storm. So any motion off, it would slightly favor negative vorticity as opposed to positive on the right side. Yes, and the question was I talking about the curvature from 1 to 3 kilometers? Yes, it's in that layer just below where the green segment starts, which is near the x-axis. So this hodograph, where the winds go from south to west, it's in that segment, and it's got slight counterclockwise curvature. So that's what we mean. So it's looping in the opposite sense. When I say clockwise, we mean as if you followed the hand of a clock, it sweeps out a curve following the hands of the clock. That would be clockwise curvature. This would be in the opposite direction, so if you flip that around, it's the opposite sense of curvature, which if you take a storm propagating to the left of the hodograph, that would actually favor anticyclonic rotation more than cyclonic. Okay, so let's look. There's the mean wind is marked on this hodograph, so that's the motion of the initial updraft before we have any propagation. There's no rotation involved. Again, right-hand rule, the hodograph itself is the connection of the sphere vectors, so the right-hand rule says the vorticity vector is always going to point off to the left, in this case, the direction of your right thumb, which is toward the northeast. Now, we put in the storm relative wind at that level, the vorticity vector is essentially perpendicular to it. So that's another way to describe crosswise vorticity. Because you notice the orientation. The storm relative wind is oriented at 90 degrees to the vorticity vector. So this is one where you'd say you should expect to see splitting storms and you won't see strong rotation initially. You won't notice that until you see the propagation take over. Okay, so here's the case of the radar. What actually happened in this one? Again, this is in the morning, elevated left split. Probably the least common storm type, but whatever reason, that's the one I found. Okay, so we watched this updraft. You already see the split process here. You see two higher reflectivity cores, and in this case, the left propagating portion is actually the better organized and the more intense. The right mover actually just dies. So the hodograph, it's perhaps that counterclockwise curvature above the surface in the inflow layer to this storm, perhaps slightly favored the left mover. And then if we look aloft, we'll look at some of the sort of deeper updraft. You just see that it's a much stronger reflexivity signature up in the mid-troposphere. It's a very weak updraft and precipitation core formation with the southern one. And in case anyone wonders, that's that three-body scatter spike that you often see with large hail, is sort of a secondary feature on this one. So it's clear that the potentially severe storm in this case was the left mover, but you could anticipate it based on that proximity sounding that it might be an elevated splitting storm environment. Okay, curved hodograph. Now we're talking about tornadoes. This is the one where it starts getting a little bit more interesting because it's much more direct, where we get to strong rotation. Because ultimately, if you want a tornado, you want strong low-level rotation. It's not just, it doesn't matter so much about what's going on in the mid-troposphere. We want it down closer to the ground. What's the big difference with the curved hodograph? I mean, I stated here, but if you think about it, we don't have the intermediate step with the crosswise vorticity. The initial vorticity for a cell moving with the mean wind is already streamwise. And again, if you have large clockwise curvature, and I'll show the example I'll show will have that, you immediately favor the cyclonic storms. If you have counterclockwise curvature in the northern hemisphere, you favor the anticyclonic storms. All right, so let's look at a sounding. This will be a classic right-moving tornadic supercell sounding, and we'll kind of come back to the ingredients here. But so you notice this appears to be rooted at the surface, large buoyancy, varying wind profile with height. The hodograph itself, that is a classic example of the sharp clockwise curvature with height. Actually, this has that familiar sickle shape that you see in a lot of violent tornado events. Not always, but it seems to be characteristic of at least plains violent tornadoes where the hodograph is oriented almost straight north-south. The important thing there is when we put the mean wind, which I mark here, this is just one estimate of the mean wind, and then you look at the horizontal vorticity vector, again, use the right-hand rule, look at the storm relative wind compared to the vorticity vector now, and this is just for the mean wind. There's no propagation at all. This is with the initial updraft motion, not encountering any propagation yet. Is that crosswise or streamwise? It's streamwise because the storm relative inflow is oriented exactly parallel. It's the same orientation as the vorticity vector. This means the initial vorticity for the updraft is streamwise. It's cyclonic, so it would immediately be rotating cyclonically, and we can show you how that looks on radar. These images, I think, are 10 minutes apart. This is the initial storm formation with the Pilger, Nebraska tornado cluster. And you notice so we have already starting to get some sort of evidence of cyclonic curvature, maybe an inflow region on the south flank of the storm. But watch when we get to the velocities, again, focus on this area. We also see what looks like a bounded weak echo region starting to form. This is in 10 minutes. So this is very early in storm formation. You look at the velocities, you go from just very weak cyclonic shear to a strong mesocyclone, 10 minutes. Essentially, it's on the time scale of one updraft pulse is all it takes in these cases. So the point here is anyone who was out and saw that one became tornadic very quickly. It didn't sit around for 3 or 4 hours going through a lot of evolution. We jumped right past a lot of the unnecessary steps, and this is, again, an immediately cyclonically rotating updraft. Okay, so hopefully that makes sense. The important thing about this is we're going to come back to why we would use these concepts and how we'd use them in a forecast sense. Okay, one question that occasionally comes up in this is supercell formation versus persistence. Does the environment of a supercell influence development differently than storm dissipation? And the question here is perhaps yes. Now, we don't have a lot of work done. If somebody wants to do some work on this is one of those areas ripe for additional investigation. But once you establish that pressure perturbation, you've got a storm strongly drawing air into the updraft region due to that mid-level pressure perturbation. The stronger it is and the closer it is to the ground, the more enhanced that effect will be close to the ground, and it can keep replicating itself. And it can do it in relatively meager buoyancy, as long as the vertical shear remains and the pressure perturbation itself remains, which again is largely a function of the vertical shear is the source of the vorticity. So storms occasionally can go into much weaker buoyancy than you would think if they are established, if you have a mature supercell. But that may be a different answer if you're talking about how do storms form. Do you frequently get tornadic supercells developing where the largest ML cape is 100 in the entire regional environment? Not so much. But you see storms move into environments like that all the time after they've formed and matured somewhere else. So it's just something to keep in mind that you can't apply the environment arguments identically because these are two sort of different questions that you're trying to answer. Okay, hopefully the whole supercell process makes some sense. Now we want to talk about tornadogenesis and try to break that down into essentially two simple modes of tornadogenesis, or I say simple, the supercell part is still a little tricky. But the idea here is that getting a tornado in the first place isn't that hard. You just need vertical vorticity and stretching. So you need some vorticity to amplify. Question is, how do you do that? Again, here's in the background, you see a picture of, so-called landspout tornado, these non-mesocyclonic tornado, pretty typical visual characteristics. Not all of them. That doesn't necessarily mean you can say that it's non-mesocyclonic just because you look at some hollow dust tube. That by itself doesn't say anything. But the point is that's characteristic of non-mesocyclone tornadoes. All they need, source for vertical vorticity. Doesn't have to be anything fancy. You just need some swirl down near the ground, and then we need something to amplify the swirl. So we've got to stretch it. So we need a spin, and we need something to stretch it, which would be an updraft sitting on top of it. Again, now this one gets pretty dicey when you start, especially me as a national forecaster. I can forecast for 48 states. The whole summer, how often could I rule out there being vertical vorticity co-located with an updraft out of 1,000 to 10,000 thunderstorms a day? How often can you just completely rule it out? What scenarios do you think you can essentially rule out tornadogenesis? Can anyone think of what's a scenario where, okay, it's probably not going to happen? Okay, like the case that was mentioned, elevated, that left mover case we showed before where there's no buoyancy at the ground, that's one likely case where we just don't have credible evidence of tornadoes with elevated supercells or anything, or elevated convection in general. However, think about Florida, the Gulf Coast, the high plains, every thunderstorm updraft that's rooted at the ground, and there's any little swirly around, a sea breeze, swirl around around terrain. I mean, maybe even something as innocuous as Mount Scott, the Black Hills, sea breeze boundaries, other thunderstorm outflow boundaries. There's all kinds of things. Collisions of boundaries. It's a nightmare when you're trying to look at down on that scale. And what are the scale of the swirlies? They can be pretty small. So the point is, you can get a tornado from almost any surface-based thunderstorm. And sometimes you see events that look just like that. It's like, wow, if it can occur with that one, it can be with anything. All you need is vertical vorticity with an updraft, and it can be on the scale of just a few kilometers across. How widely spaced are our observations typically? Even here in Oklahoma, how far apart are the mesonet sites? 30 miles-ish, something like that. Is that good compared to the rest of the country? Tight space, that's great. I mean, you have a few other places that are similar, and we have more observations now than when my career started, but the idea is these swirlies usually can occur on much smaller scales, even than the mesonet can observe. But that doesn't mean it's a hopeless cause, so we can still forecast some more obvious mesoscale patterns to favor non-mesocyclone tornadogenesis. Now, the important thing here with supercells, which will be the second part of the tornadogenesis discussion, is that supercells create, essentially on the storm scale, they create the vertical vorticity themselves. The stretching and the vertical vorticity generation are the result of internal storm processes. So essentially, supercells kind of create their own environment, but they are in turn related to the background environment. So they're not separate from the environment, but in the right environments, they essentially create conditions on the storm scale that provide vertical vorticity at the ground and strong vertical stretching. So you tend to get the longest lived, strongest tornadoes with supercells, but tornadoes are actually probably more common without mesocyclones if you just look at it globally. Okay, non-mesocyclonic tornadoes. Again, a swirly on a pre-existing boundary. The boundary itself is the vorticity source. What else is the boundary the source of? It's usually a convergence zone. It's a source for updraft formation. So it's really not a surprise that you're looking for some kind of boundary. Now, again, there's other terrain and small-scale features that you're going to hardly be able to pick out of the weeds, but in general, we can find more mesoscale and synoptic scale boundaries that are occasionally linked with sort of serial non-mesocyclone tornado formation. You get multiple events in sequence. And again, if you just get an updraft to sit long enough over a swirly, you can get a tornado. It's just a function of how strong is the updraft, how strong is the initial swirl. Okay, this is the familiar graphic, sort of an illustration of the process from Brady and Zook. This dates back to the Denver cyclone stuff. This is, essentially one of the more tornado-prone areas of the world is just that area just northeast of Denver, Colorado, which is a terrain-based circulation that is the vorticity source, and it's also a zone where thunderstorms tend to form. So mid-afternoon, June especially, you tend to get updrafts co-located with this vorticity source. You get weak tornadoes. Typically, they're weak. All right, So we continue through. You also see these occasionally in sequence. I wish I could say these are my pictures, but they're not. You get strings of tornadoes. Some of these may be other forms of instability along boundaries, but it's pretty common. Actually, we had this, was it Friday in southwest Kansas this past week? So there was actually a case with 2 or 3 tornadoes ongoing simultaneously. There was a little cyclonic shear boundary and a storm sitting on it. So it was a whole sequence of tornadoes formed somewhat equally spaced. So this sort of thing happens pretty much every year. Somewhere out in the Great Plains you can find one of these. And so we'll go through a case of a non-mesocyclonic tornado and show you how it lines up with the background environment. Okay, here's one. We want to focus on the Kansas-Oklahoma border, especially south central Kansas, right there on the Oklahoma line. This is near the time of the event, so we're just kind of doing a diagnostic look at the environment. This isn't a forecast. You notice there's a weak shortwave trough, mid-troposphere. This is 500 millibars. But the strong flow is to the northwest of where we're looking. So there's 40-knot flow back over the high plains and over parts of the central plains, but not down where the surface boundary is. So the flow aloft is relatively weak. Low-level flow itself, not that strong. Again, you wouldn't expect a real strong Lee cyclogenesis response in this scenario. And this is an August case, by the way. So synoptically, it's not obvious that this would be a supercell environment. However, we do have a surface boundary that's related to the synoptic system. I've sketched it in blue there. It wasn't really a cold front. It was more or less a stalled front. Notice that the temperatures are maximized right along the boundary. The winds go from north or northeast on the west side of it to south or south-southwest on the east side of the boundary. That's creating vertical vorticity in that whole zone, and dew points are maximized up into Kansas in the low 70s. Same corridor, we have vertical shear. If you look, it's all to the northwest of the boundary. Now, we haven't really talked specifically about what measures. This is just the fixed layer, 0 to 6 kilometer bulk wind difference. Anything that the way we scale this on the SPC mesoanalysis page, we tend to plot the values that are in the range of the parameter space favorable for supercells. So if you don't see barbs or contours, we tend to be a little bit too weak, and you notice it's all on the cool side of the boundary. But buoyancy is maximized right along the boundary. And as you go up toward southern Kansas, the convective inhibition is weak. So we have large cape, relatively weak vertical shear, fairly high moisture content. And if we continue looking at other elements, we do have relatively steep low-level lapse rates. So we've got an environment you could see thermodynamically that would favor thunderstorm development with steep low-level lapse rates to reduce convective inhibition and sufficient moisture and large buoyancy atop that. So this is, and we do have a boundary to provide some background source for lift. The lift is related to here, the red contours would be convergence. This is just, again, depends on the scale of the analysis. So, you got to be careful about using these magnitudes of convergence compared to something calculated from different data sets. So it depends on the grid spacing is kind of what kind of answer you'll get here. But here there's vertical vorticity in the shaded areas. So if you look, there's a max, kind of south central Kansas, convergence and vertical vorticity appear to be maximized. That's also where buoyancy was large, inhibition was weak, deep layer vertical shear is weak, and it's on the nose of the steep low-level lapse rates. All right, so here's what was happening near the same time, and I'm pointing to the arrow, which is where the tornado will form shortly. We notice we have a band of thunderstorms. The north-south green band that's near the radar site, that's the depiction of the front itself. So that's the stalled boundary denoted in the low-level reflectivity field. And then there's an outflow associated with the convection that intersects that boundary. You kept getting new thunderstorm formation where the two boundaries intersected, and that was developing southwestward with time. So we'll kind of look at that. You see the convection, the echoes developing southwest. Again, we go aloft. You see stronger updrafts, so there's deepening updrafts above this that you see in the higher elevation cuts first. Low levels, there's just very weak cyclonic shear. You follow this, but you look aloft and you start seeing a little couplet shows up. So this is amplification of this weak background vertical vorticity that's sitting on the boundary. And before you know it, you've got this tight little velocity couplet, which is on the 88D scale and a range of only 30, 40 miles. It's a reflection of the non-mesocyclone tornado, which in this case actually looks like a pretty standard tornado. So notice it's not a hollow dust tube or anything else. There's no hint of supercell structure in these storms. This is just a function of moisture content. So we get a You get the pressure deficit in the tornado itself. You get condensation because it's a moist environment. So again, don't get too hung up on what the tornadoes look like. The point here is you don't have all the characteristic supercell structures around it with a clear slot, a mesocyclone, and a deeply rotating updraft. And this, Kansas seems to be a hot spot. As I mentioned, just here in the last week, there was a scenario similar to this occurred. Now, it was mixed in with a bunch of other storms, and you have to pay pretty close attention. Sometimes, in my experience, you get sequences of these type events. When you look at it, you might look in midday and say, oh, this isn't a supercell setup, so I forget it. But you've got the boundary sitting there. So you can kind of watch, and sometimes these would be considered secondary targets. Because what's one good thing about these sort of storms? They don't move very fast. The vertical shear is weak. If the storms sit on the boundary, they're really easy to chase. You just drive up and sit there. So if you want a low-stress chase, find one of these boundaries and just hang out till storms form, and you might get lucky. Okay, now limiting factor. What can short-circuit the process of non-mesocyclonic tornadogenesis? The big one is if it's too stable near the ground. And usually that's related to precipitation, formation, and outflow generation by the convection itself. If it produces a lot of rain and a lot of cold outflow really quick, it'll tend to undercut everything. So what you're usually looking for are the newer developing updrafts, not the mature storms producing a bunch of rain. Or if there is just enough vertical shear or flow in the environment, if the storms move off the boundary too quickly, they may not have a chance to amplify the vorticity. So you want updrafts sitting over the vorticity source as long as you can get them to stay there. So hopefully that makes sense. And again, it really isn't any more complicated than that. Tornadogenesis, even in a supercell, it's the same kind of thing. You've got a stretching source co-located with vertical vorticity. The trick is how do we get those two in the supercell compared to the non-mesocyclone cases. Okay, well, there's my segue into the mesocyclonic tornadoes. These are the serious ones. This is why most of you are here. These are, the more popular storms. Again, I showed you at the very beginning, they do the disproportionate amount of the damage from tornadoes and large hail or with supercells. This is just a classic radar 4 panel from the Valonia, Arkansas F4 producing tornado from last April, just over a year ago. And again, all the characteristic structures there, you see in the low levels a very strong velocity couplet in the upper right, reflectivity signature associated with it, aloft, a large bounded weak echo region atop that with broad, strong rotation reflective of the mesocyclone. So we've already discussed how you get these basic structures in the supercell. So what is it about this structure of a storm that favors tornadogenesis on occasion? Okay, so again, just think back to the vorticity sources. We've got the right-hand rule. You've got the vorticity vector in the direction of your thumb. You think of storm relative helicity, which is, we talk about measures of vertical shear. That's one of them. That's a way to quantify the magnitude of these vortex tubes. And then we have one other thing that we have to consider here is baroclinic vorticity generation. So this is the generation, essentially, another way to say it would be frontogenesis, something like that, where the response of the environment to a tightening temperature gradient, in this case, it's related to the storm itself, the transition between the inflow region and the precipitation in the storm. Okay, so mesocyclonic tornadogenesis. We first start with the supercell part. We want a persistent rotating updraft. Again, we discussed this, buoyancy, deep layer vertical shear. We do need some low-level vertical shear, but the idea is it's sort of a cape shear combination, gives us the supercell background environment. The pressure perturbation associated with the rotating updraft is what induces low-level storm inflow. It strengthens the inflow and it strengthens the updraft down closer to the ground, somewhere below the pressure perturbation. And if you can get this strong enough and low enough, that can really amplify the stretching term all the way down near the ground, if you can do that. But again, this still leaves us with where's the vertical vorticity come from in the supercell? We looked at the case with the stalled front. It was the sheer vertical vorticities generated along the boundary itself. How are we doing this in the supercell? So I just want to reiterate that it's not storm relative helicity that's doing this directly. It's not the horizontal vorticity due to the background vertical shear. Because with tilting and stretching alone, the only way you can amplify horizontal vorticity through tilting in an updraft is away from the ground. So it tilts it and amplifies it as you accelerate away from the ground. So you can't get strong vertical vorticity at the ground due to tilting and stretching with an updraft. But what happens with a downdraft? So we'll talk about that some more. So again, it's not storm elasticity. It's not a direct relationship between strong low-level shear and tornado formation. It's actually indirect through what it does to the pressure perturbation. Again, the rear flank of the storm and downdraft zones seem to be what are critical for the formation and redistribution of vertical vorticity in the storm that ultimately supports tornadogenesis. It's the rear flank downdraft. So we've got to know something about the characteristics of the rear flank downdraft, because still, the basics of tornadogenesis hold. We want vertical vorticity and we want strong stretching. We don't want anything to resist the stretching, and we actually have to have the vorticity about a vertical axis. So we've got to either reorient vorticity and have buoyancy, or some combination of those things if you want a reproducible tornado setup. Okay, so these graphics are courtesy of Paul Markowski from Penn State. It's as good as anything I can find out there as far as trying to illustrate the process. And this is probably the most complicated part of the supercell tornadogenesis process, is the reorientation of vorticity into the vertical from the horizontal. And this is one that I'm going to admit straight up, I think I about 80 or 90% understand it, which maybe 6 months ago it was 65, 70%. And I don't know how many people truly get this. Down on the nuts and bolts level, there may be a handful wandering around the US or the rest of the world that really, truly understand this right now. But from my personal observations, it does work. So there's clearly a relationship to what's happening in the real world. So the idea here is that you need a downdraft to get vertical vorticity to the ground. And it's through tilting, but it's tilting in a downdraft as opposed to an updraft. Because what's the orientation of all the vorticity due to the background vertical shear? It's horizontal. So the right-hand rule, these are all horizontal vectors. Now what happens when you have air that's moving along a temperature gradient? Is vorticity being generated as the air is traveling in a temperature gradient? That's frontogenesis. Now, in this case, the question is you have to think about which direction is the vorticity vector associated with the frontogenesis. Let's think about a supercell. Think about the picture we have on the screen there. Where's the cold air associated with the precipitation in the storm? It'd be in the background, right? So it's behind the ice skater illustration. Where's the warm air? It's in the foreground. Okay, what's the frontogenesis response in that case? If we're tightening the gradient because we're producing heavy precipitation and cold outflow generation right next to the storm inflow, we've tightened the temperature gradient. Okay, so what happens, what's the direction or the frontogenetic response? What's the response of the atmosphere to that scenario? What does the atmosphere try to do in terms of frontogenesis? We talked about this in session 1. Is it trying to strengthen the gradient, reinforce what the storm's doing, or is it trying to weaken the gradient? It's trying to weaken it. And that's normally the atmospheric response, is to try to undo this imbalance that's been created. So in this case, how do you weaken the thermal gradient? Anyone remember the frontogenesis? What's the response to frontogenesis? Where's the rising air response? It's on the warm side of the boundary. Knowing just that alone, you can use the notion of there's a circulation associated with these frontogenesis responses. Sinking on the cold side, which is an adiabatic warming process, rising on the warm side. Sinking on the cold side, rising on the warm side, and again, adiabatically, you're cooling the warm side and warming the cool side. That circulation, the right-hand rule, the vorticity vector points back. In this case, if we're looking northwest, the vorticity vector points back to the southwest. So it's parallel to the forward flank boundary of the storm. So it's generating vorticity vectors that point back toward the mesocyclone. Now that may be a source for vorticity that can be tilted and stretched by the low-level updraft. And you can get a positive feedback going. So essentially have you ever seen the tail cloud feature on a storm? That's a visible manifestation of that thermal gradient. And you are generating vorticity along those zones, and the storm's literally scooping up that vorticity. That's highly streamwise vorticity, but still, it's amplified above the surface. The key here is as you're moving west or southwest in this case, along that gradient, if that air is also sinking in response to the downdraft, it would try to point the vorticity vector down toward the ground, right? The initial vorticity is horizontal. It's just going to try to reorient this. But what is also happening in response to the thermal gradient the entire time the air is subsiding? You're generating new vorticity baroclinically. What's the orientation of that vorticity that you're generating baroclinically? It's always horizontal. So you're changing the orientation of the initial vorticity vector, but you're adding this other horizontal vorticity vector to it. You bring that to the ground, and now you're not tilting anymore. You actually have a vertical component of vorticity now. So it's all due to adding this baroclinically generated vorticity during the sinking phase of these parcels flowing along around the forward flank and the rear flank of the storm. So again, it's pretty complicated. I'd encourage you to just think about it some, look back over some of these, download the PowerPoints, and just think, because it is pretty complicated. But the notion is, it appears to be that temperature gradient that generates the vorticity, and because you're reorienting it with a downdraft, you transport this to the ground, you're adding more vorticity as you go. By the time you get to the ground, you've actually got some component that's vertical. Now we've got vertical vorticity. If that air is buoyant and you superimpose that with the low-level mesocyclone and strong stretching due to the pressure perturbation aloft, you can amplify it into a tornado. Okay, so the point here is that we have some environmental clues that can be linked to this stuff that we can look at. So in this case, if the pressure perturbation is too weak, then the low-level updraft is going to be weak. If the pressure perturbation is very strong, then the air is drawn in strongly and stretched strongly. That is where storm relativisticity comes in. The more horizontal vorticity you have closer to the ground, and it can't even be related to the forward flank itself. The stronger the storm rotates closer to the ground, the more favorable it is for the stretching term in the vorticity equation. Okay, so Paul's illustration talked about, air that it's not too cold in the low levels and there's strong suction from above. I just mentioned that one. The problem here is we don't have direct measurements of this stuff. There's not mobile mesonets floating around on every storm, and we certainly don't have measurements every 100 meters or something that we'd really like to have. But we can get these from the background environment, from remotely sensed data that can tell us something, give us some statistical sense of what might happen. So let's look at the supercells. We'll kind of look at this whole process and think of that, and I'll show you the motion of that vorticity vector, which might make a little more sense here. So we've got rotating updraft that's a function of the background vertical shear. So in this case, there's also a veering wind with height. I like Paul's illustration with a football, so I'm a football fan. So this would just be tilting and stretching, horizontal vorticity, big rotating updraft. Now, the vorticity source for the supercell mesocyclonic tornado is on the rear flank, where it's related to these gradient zones in the storm. In this case, if you have a general downdraft associated with the edge of the precipitation, this is that frontogenetic response. So the vorticity vector is oriented back to the southwest, and because we're moving along, now we're tilting it. The key here is you notice the change in the orientation of the vorticity vector through tilting and new generation. So we're constantly generating new horizontal vorticity and tilting it at the same time. It's because the orientation of the tilting, we're tilting it back down toward the ground. So we're slowly reorienting this over time. Now again, this is a simplified version. It's probably a little more complicated to get down mathematically to show all of this, but the point is you're generating vorticity and you're reorienting it, and it appears to be related to the rear flank downdraft. So we need to know something about the precipitation characteristics. We need to know something about the downdraft itself. How much vorticity do we generate, and how easy can we amplify it? All right, the strong suction from above, again, that's mesocyclone strength. You can measure that with radar. And if you get the strong rotation close to ground, you actually have a strong forced updraft close to the ground. Okay, so what do we observe? And I'll show a real-world example of what happens. We see the strengthening of the rotation aloft. If you have pressure observations, surface obs in the right place, you'll actually see surface pressure falls in the vicinity beneath that. You'll see accelerated inflow, and sometimes you'll even see the really laminar, strongly forced descent. These real sculpted supercell looks that are a function of forced descent. That's air that is not rising because it's buoyant. It is being forced, and you're overcoming inhibition. Okay, so we're going to look at the El Reno storm, which is kind of a high-end example of it, but that's the point, is to show one that's pretty obvious early on. Here's what we're looking at is the storm relative velocity. You could do this with base velocity as well. It's just subtract the storm motion out of it. In this case, this low-level storm inflow at about 3,000 feet was out of the east at about 65 knots at this point. What happens over just 10 or 15 minutes, the storm inflow is increased to a peak of 82 knots. So we've gone from minimal hurricane force storm relative inflow to now, 65 to 82 knots is pretty good, just over, it's accelerating by more than a knot per minute, which is a pretty big increase. And you notice the size of the area of the storm inflow has increased, the orientation has changed. What's going on aloft at the same time? Now we calculate the rotational velocity here. This is just the difference between the peak outbounds and the peak inbound velocities. In this case, 58 knots. That's more familiar to you, might be a delta V of 116 knots. So there's 116 knot velocity difference. That's pretty strong aloft. But again, just less than 15 minutes later, it's up to 70 knot rotational velocity. So now our delta V is 140 knots. This is the exact same time you've seen the increase in the low-level inflow. We've got a huge increase in the rotation aloft. They're related. Same time, we have this big echo. There's an updraft that has gone up. You look at what happens to it aloft. We develop a large bounded weak echo region. This is just the updraft is so strong that precipitation particle formation is delayed. You don't even see it in the mid-troposphere. The particles end up way aloft before precipitation can even form. So you see this weak echo donut hole, and that's usually a sign of a very strong updraft, which is right there with the mesocyclone and right above the strong low-level inflow response. And then, of course, the storm rotates more strongly, and you start seeing the change from sort of an amorphous blob to the standard appendage and supercell reflectivity shape. So this is all preceding tornadogenesis. This is the stuff that's happening in that 15 minutes leading up to tornadogenesis. I believe in this case, if we go back, you can actually, if you look real close on the left side of the circle, you see that real tight velocity couplet down low. That's the start of the tornado. So the mesocyclone is much, much bigger than the tornado. And in that particular case, if you know anything about the tornado, that's kind of scary to think about, is the mesocyclone. The tornado wasn't really even small at the beginning, and the mesocyclone dwarfs the tornado. So this is just a pretty you can find other examples. That Valonia, Arkansas case, you can see the same sort of evolution. So it's not unique to just the Great Plains. All right, what do we mean when we say not too cold? We're talking about if we've got strong low rotation, strong forced updraft, we still have to be able to amplify that vorticity that we generate. So we don't want air in the low levels that's strongly resistant to the stretching term. So think of it this way, it's sort of like if you're doing, sort of weightlifting, you got to lift a dumbbell up. Is it easier to lift a light dumbbell or a 200-pound dumbbell? There's a couple of people I know that maybe the 200 wouldn't be that bad, but me, it would be bad. So the idea is you want to reduce the resistance to the ascent in the low levels, in the stretching term. So how do we deal with that? How do we quantify something like that? So we know it originates, this air appears to originate in the RFD. We know that's where the vorticity is generated. So how do we say something about the resistance to stretching? Well, if this air is really cold and really stable, which means we don't have a lot of CAPE, we have a bunch of convective inhibition, it's going to be difficult to amplify no matter how much vertical vorticity there is. Now this brings up a bit of a conundrum. When would vorticity generation be the strongest? When the temperature gradient is weak or when it's strong? It's when it's strong. When the temperature gradient is very strong, what's the likely characteristic of the storm outflow? It's very cold and it's very stable. So you're kind of between a rock and a hard place here. You're trying to balance two opposing processes, and what that suggests is there's some middle ground where you've got some thermal gradient to generate vorticity, but you also have buoyancy. And what's another thing that would be counterintuitive? Think back to our discussion or anything you've seen in class or in person with thunderstorms. What's the purpose of the thunderstorm updraft? What is a thunderstorm trying to do to the environment in a general sense? Stabilize it. And that's right. So you're trying to take warm, moist air into the ground, transport that upward and outward, and you're trying to take relatively dry, cold air aloft downward and outward. And that stabilizes the profile. So you want to get rid of steep lapse rates. You want to get rid of an excess of moisture near the ground. And that's what thunderstorms generally do. They're good at it. In particular, some of these supercell thunderstorms appear to be not very good at that at all, which is a unique situation for a thunderstorm. In other words, they don't stabilize the profile very effectively. Because we're talking about, we want a parcel in the rear flank downdraft that's not resistant to stretching. That means we want a downdraft parcel that's buoyant, which is counter to most of what you see. If you were to go outside and take measurements in most thunderstorm downdrafts, they're going to be strong negative buoyancy. No cape, all convective inhibition. So it's kind of a special case that we're looking for. Well, what suggests that that special case is there? Well, you want something about the environment to reduce cold pool formation potential. One way, and we're talking in the low levels, we're not talking about air that originates way deep in the storm. We're talking about air that originally starts not too far from the ground. It's original inflow air into the storm, around, and then back down. One way to reduce cold pool formation is to be very moist. There's no evaporative cooling potential if it's a moist environment. So to get a relatively warm rear flank downdraft, you want high moisture content in the low levels. That reduces evaporative cooling. And what does it also do simultaneously? What is the biggest contributor to buoyancy aside from lapse rates? Is it temperature or moisture content? Which one increases buoyancy quicker? A 1 degree increase in temperature or the dew point? Dew point. So the mixing ratio, it's very effective. So what high moisture content does is tends to push you to bigger cape, all else being equal, and it also reduces cold pool formation in the low levels. So what we're doing is we're looking for a special case. You can already sort of see the recipe here. We want strong low level shear and deep shear to get supercells. We want the rotation close to the ground. And then we've got to have the boundary formations within the storm. That's kind of a tricky part based on the environment. The best we have been able to do to this point is to use something like low level relative humidity or LCL height. So low LCL environments with strong deep layer and low level shear, lots of clockwise curvature in the hodograph, and high moisture content tend to favor significant tornado formation. Okay, so we'll go back again just to summarize with this one. The idea is that if the air's not too cold and there's strong suction from above, you can amplify to a tornado. What does it look like with the observations we have? It actually matches up. You look here at the top. These were from the Vortex projects. I think this was mostly from the first one. The idea here is that you've got these, you see some outline of a particular reflectivity, so that would be some lower reflectivity values. So you see the characteristic hook shapes, little curlicues there. Notice the color coding in the background. It tends to be the shades of pink in the vicinity of the low-level appendage. That means the air in the rear flank downdraft that was sampled directly with mobile mesonets was relatively similar to the inflow air in terms of buoyancy. So it's not cold compared to the inflow air. You go to the non-tornadic cases, at the bottom, you see all the dark blues. Those are ones where the perturbation is much more negative. It's noticeably colder than the inflow air. So that's a case. And you notice another characteristic of the non-tornadic storms. You notice the appendage is much thicker. For the same reflectivity threshold, you have big, fat hook echoes. There's a lot of precipitation on the rear flank, which is another contributor to strong cold pool formation. Whereas a lot of the most intense tornadic storms sort of have an intermediate or lesser amount of precipitation around the mesocyclone. That's just something else to consider. But again, so what we're trying to do is we've got this case where you've got competing factors of a cold pool formation versus maintaining low-level buoyancy. The idea is that you want sort of a happy middle ground, and it's rare. It should sound like a rare set of circumstances, and it is. That's why every storm doesn't, there are hundreds of supercells for every handful of them that produce long-track, stronger violent tornadoes. So the point is, it's hard to get this set of circumstances in place to favor tornadogenesis with mesocyclones, or certainly more than just weak tornadoes. But it's important because from a forecast perspective, the vast amount of damage, destruction, injuries, and deaths are the result of just a handful of tornadoes a year. You go back to like 2011, I mean, we had nearly 400 people killed just by something like a dozen tornadoes. So there's 500 people killed in the US that year, 550 I think. Probably 80% of those were just by a handful of storms that produced really big, really intense, long-track tornadoes that unfortunately made their way into population centers. So it is critically important to be able to reliably and accurately forecast those kind of events. And that's really what drives this conceptual model. Okay, we'll look at another way to consider this is that if you don't believe me that the buoyancy part matters or whatever, these are forward trajectories using, again, detailed examinations of these storms. What you see here is you notice all the lines, these erupt upward. This says that they're releasing air parcels from that airstream and they end up feeding the deep updraft in the storm. This is the case with the relatively buoyant rear flank downdraft. So that is downdraft air that is being reprocessed in the low levels, pulled in, and it actually is being processed in the updraft. The non-tornadic storms, look what happens to them. They're pulled up. The pressure perturbation, it tries to draw that air upward. You see a little bump, and almost none of them make it. So the idea here is that air is not feeding the deep updraft. So what we're really looking for is air with a lot of spin, originating from a downdraft that can feed a deep, strong, rotating updraft. It's a weird set of circumstances, but supercells, in particular with strong shear and moist environments, tend to reproduce this more frequently than anything else we can find. All right, so again, the rotation is weak, close to the ground, the suction's weak, or if the downdraft is cold, either way you can short circuit the tornadogenesis process. If the pressure perturbation is very strong, the suction of the air in from below is very strong, and if the outflow air is relatively buoyant, then that would be the positive feedback and you get tornadogenesis. So again, we don't have direct observations of this stuff, and what corresponds to not too cold in the environment. I've already mentioned it, but we'll just mention here, the notion of LCL, it is one measure. It's one thing that we've looked at. Does it explain all of the variability? Of course not. But it does a remarkably good job for as simple a quantity as we have. And what's nice about something like LCL height, you can base this on surface observations, which is our most dense observing network. You can use temperature dew point spreads. You could use low-level relative humidity. In this case, we're using the 100 millibar mean parcel LCL height, but that's just to be consistent with the buoyancy calculations and everything else. Again, moist environments favor weaker downdrafts, more buoyant air in the low levels. Near the storm's low-level mesocyclone, that can be stretched and amplified in the right circumstances. So it's a positive feedback. So again, this is where we kind of tie it all together. You're looking for the positive feedback for significant tornadoes. You want sufficient buoyancy and vertical shear to get supercells, so you've got your long-lived rotating updraft. That reproduces itself, so now we look to the low levels. If the pressure perturbation is strong and it gets down close to the ground, we end up strengthening the low-level inflow and forced descent. If we can do that in the presence of a downdraft that has vertical vorticity has been generated on its path to the low-level mesocyclone, if it's relatively buoyant and there's a lot of spin with it, you can amplify it rapidly into a tornado. And again, it's close. If you go out and look at storms, you see all sorts of, close but no dice type scenarios where you can guess that it's either the outflow's too cold, the spin isn't strong enough, the suction term isn't strong enough. There's no way to quantify it right now to say, oh, well, if I have this degree of rotation at this elevation above the ground with this temperature dew point spread, I'll get a significant tornado every time. No, it's more of a probabilistic argument. When you get this set of circumstances to line up with individual storms, the probability of long-lived and/or intense tornadoes increases, but it's not a guarantee. You can find failure modes in environments that look like this, and you can occasionally find significant tornadoes in environments that don't meet these conditions. So again, just to summarize where the air's coming from in the storm, we've got the inflow environment. This is related to the supercell part. So just kind of the background environment. Do we get a supercell or not? Because it's important to have a reproducible storm structure. Low levels, this can be related to, it's either this one or the background environment. How strong is the rotation in the low levels of the storm? Because remember, if you're generating vorticity along the forward flank and that's feeding the low-level updraft, that's an additional vorticity source beyond just the ambient horizontal vorticity. So in that case, you can actually strengthen and lower the pressure perturbation due to an impact of the storm itself. And then, of course, the tornado, it all appears to be related to what's going on in the rear flank of the storm. So you just got to kind of think about the storm, that there are different processes acting in different parts of the storm, and think of this as a probabilistic exercise because there's nothing deterministic about it at this point. We can't just say with complete confidence that this storm will produce a tornado and that one will not. And again, just to summarize the basic ideas, do we have a supercell environment? Does the forward flank inflow region favor amplification of the low-level mesocyclone and bringing the pressure perturbation closer to the ground? And do you get the right kind of rear flank downdraft so that you can generate a lot of vertical vorticity and amplify it in that low-level updraft? So it helps to have all of these processes acting in tandem. So again, that sort of sums up the whole supercell tornadogenesis thing. We'll take a couple-minute break here, and then we'll try to look at some of the applied parameters and where they come from and why we would want to use these in these environments. So we'll take a break, just a couple of minutes, and then we'll start the second half, or second third. Yeah, the last third, whatever it is. All right. Oh, now we're good. I see. There's something familiar about this again. We will wrap up the session here with a discussion, partially for a second time, on some of the parameters related to supercell and tornado formation. So how do we forecast supercells and tornadoes with a coherent conceptual model backing the forecast process? The necessities. We need initial buoyancy to support an updraft. That one should be fairly self-evident. We need vertical wind shear to produce a rotating long-lived updraft. We need to tilt and stretch the horizontal vorticity generated by the ambient vertical shear. That's what essentially sets the stage for the supercell. And the fact that it's a rotating storm tends to make it a longer-lived storm. Okay, so when we apply these concepts in the real world, we need to know a few other things that we haven't necessarily talked about. I mean, buoyancy is pretty straightforward because we have a way, we calculate CAPE. I mean, the calculation itself is fairly involved, but there's a lot of sounding routines out there that do this for you, incorporate things like virtual temperature corrections, that sort of thing. You have to choose which lifted parcel. There's some complexity there, but the idea is we have ways to deal with buoyancy. Vertical wind shear, the question becomes, what vertical wind shear? Through what depth? We've talked about low level and deep layer without actually defining what we mean by those. So we're going to have to look at that question in a little detail. So we need enough horizontal vorticity so that we can create low-level rotation in the storm so that we can amplify this. Question is, how much is enough? And then we also need enough vertical shear that we haven't mentioned to get forming precipitation away from the updraft. So you have to look deep enough so that the storm doesn't just go straight up and straight back down. That's not a long-lived storm. We need to remove the precipitation. That's another role of the vertical shear. Okay, when we say low-level shear, what do we mean? We want to represent the storm inflow layer. So it's the air that's feeding the updraft is what we mean by low levels. Now, when we talk about that, when we say the inflow layer, we're talking about the air that's potentially buoyant. It has to have cape associated with it, or otherwise it doesn't really matter. This is where the notion of the effective inflow layer comes in. I've mentioned it on a few occasions here. I showed it on the soundings with the examples, and we're going to talk about exactly what is the effective inflow layer. The idea here is that we're trying to find what layer in the environment potentially supports the thunderstorm updraft by applying some lifted parcel constraints to it. So what we did is we played around with a bunch of combinations, and it turns out a relatively conservative estimate of what the air that might be feeding or potentially could be feeding the thunderstorm updraft would be any lifted parcels with cape. Essentially, in this case, we're only looking for 100 cape. That's pretty small. And not excessive convective inhibition. In this case, the inhibition can't be larger than about 250 joules per kilogram, and the cape has to be at least 100. If you take those minimum criteria, that's pretty low end. 100 cape and 249 sin, that's pretty conservative estimate. So we're not drawing any hard line here. We're saying just could this air conceivably be associated with the thunderstorm updraft? Okay, it makes more sense when you see how this is illustrated with a sounding. This is another elevated supercell case. And what I'm going to do is we're going to lift the parcels and show you how we come up with that effective inflow layer. So the inflow layer is that little goofy blue whisker thing to the left of the diagram. That represents the top and bottom of the layer of the parcels that meet those cape and convective inhibition constraints. So we're looking at this layer. I've highlighted it for you on the sounding, and that's how we denote it on the profiles. Okay, so we start with the surface parcel. We lift that one. You notice it's all to the left of the environmental profile. It's all negatively buoyant. There's no cape. This one doesn't meet the criteria. Next parcel, we move up, and I'm just doing this every 25 or 50 millibars. So we're doing a crude version of the inflow layer. What we do in the background is we literally look at every single level in the sounding to do this. This one, this is the first parcel that actually meets the criteria. It doesn't have a ton of inhibition, and it's got enough buoyancy. So this is what we're calling the effective inflow base. We continue to work up. The buoyancy increases. We continue moving upward with the parcel, and then you notice that eventually the cape decreases as the moisture drops off. Eventually, you no longer meet the inflow layer criteria. So if you go back through that, it's just this layer everywhere where those parcels are buoyant enough and not super strongly capped. So it just happens to be that layer, roughly 900 millibars to a little bit above 700 millibars. So that's the notion of the storm inflow layer. If this is an accurate sounding, then that should be the air feeding the thunderstorm updraft. So that's the layer we're interested in, the horizontal vorticity. If we apply this to a hodograph for the same case, the white lines denote the area swept out between the storm motion, which is the little circle, the point there, moving like southeast at 15. That was the motion of the storm, and in this case, it's only the curvature in the upper part of the 0 to 3 kilometer layer. So you notice we're ignoring the shear in the low levels down below that, and that's because that air is not buoyant. So this is a worm advection case, and this is an elevated supercell, and we're looking at the potential horizontal vorticity in that roughly 1.5 to 3 kilometer layer. So that's the air that's potentially feeding the updraft. And again, that's what we call the effective storm relative velocity. Okay, now here's a plot of effective storm relative velocity. This is from some other climatological work that we've done at SBC. On the left would be significant tornadic supercells. These are radar-confirmed supercell storms. And you go across to weak tor, non-tornadic. And the one that's the most interesting here would be the elevated RM. That would be the elevated right movers, the fourth one over from the left. And then, of course, we have some marginal and non-supercell storms in there. So in this case, we're looking at the comparison of the effective SRH versus 0 to 1. So the effective SRH are these gray boxes in the background. So you notice the effective helicity tends to decrease as you go across the storm types. It's strongest and largest for the tornadic supercells, noticeably weaker for the non-tornadic, and then it collapses down to very little for the non-supercell type storms on the far right. Notice the elevated right-moving storms, which do not have any tornadoes associated with them, fall somewhere in the distribution closer to the non-tornadic storms in general. Now, if you use fixed layer shear for a case like this is what happens to your shear calculation. They look similar for the surface-based storms, but notice what happens there in the case for the elevated storms. You substantially overestimate the vertical shear because you're counting all that low-level shear where there's no buoyancy. So the idea behind the effective inflow layer is to remove the irrelevant parts of the wind profile. All right, so looking at this again, and since we're going to talk about the composite parameters to piece this all together, I just highlight the value of 50 because that's the normalization term in the supercell composite. You notice that most of the supercells are well above that, but on the far right side of the diagram, the non-supercell storms, these are discrete storms with no supercell structure, actually tend to almost always be below that. So that we choose that as kind of the background representative value as a discriminator between supercell and non-supercell. Okay, when we talk about deep shear, we have the same kind of problem. We have to talk about what layer, what's enough. Well, here, we got to go high enough to get precipitation removal from the updraft so that we get sustained storms. And the question is, how high do we have to look? How do we count for storm depth? So we do this through the effective bulk wind difference. It's sort of the same idea as the effective inflow layer, where we're trying to account for how deep is the convection, and we use that to scale how deep we look. So in this case, we are looking at the layer of the potentially what we're calling the entire depth of the storm. So we take the most unstable parcel, which is kind of the most optimistic view of the storm's depth in terms of the updraft and the equilibrium level and all that. And then we take the base of the inflow layer, which is the most conservative estimate of what the lowest the air in the profile might be feeding the storm updraft. And we combine those two and consider that the depth of the storm. So we'll go back to that same sounding that we showed. The inflow depth, or the storm depth, which is basically from the bottom of that little whisker, the bottom of the inflow layer, up to the equilibrium level with the most unstable parcel. So the white bar there highlights that's the depth that we're looking through to calculate what we mean by deep layer vertical shear. Okay, now the question becomes then, what through that layer? Where in this layer? I mean, I know you've probably already seen the effective bulk wind difference, or the effective shear as it's known, or the 0 to 6 shear. The question is, why those layers? Well, now what I have here is, we've shown some box and whisker plots. If you think of these are plots connecting the dots of the top and bottom whiskers of two distributions. So the blue one are the 90th percentile with the non-supercell storms. So that's the high-end vertical shear associated with storms that were not supercells. The red line is the 10th percentile, or the bottom whisker of the supercell storms. So the question here is, you want the biggest difference between the two distributions. In other words, you don't want overlap. And where do they not overlap, or where's the overlap the least? It's right there in the middle, about halfway up the storm depth, which is noted by 50%. The other way to think of this is, if you think of the box and whisker, the bottom whisker of one is near the top whisker of the other. So if you do a box and whisker plot, those distributions, or a scatter plot, they are widely separated. Most of the distributions do not overlap. Whereas if you go to the right part of the upper part, you look through a deeper part of the storm, the weaker, the non-tornado or non-supercell storms actually have shear that overlaps into the lower end of the supercell storms. So this is one where those two lines are real close together just suggests that the distributions are almost completely different. Perfect world, they would actually be, the red line would be above the blue line, and it actually is slightly there at 50%. So we chose, for statistical reasons, the lowest half of the storm to calculate the effective bulk wind difference. And that's, again, here in the middle of the profile. Now, the way it turns out is that if you do this with a typical warm season supercell storm, equilibrium levels are close to 12 kilometers. Storms are surface-based. What's half of that depth? 0 to 6 kilometers. So it ends up replicating the 0 to 6 shear the vast majority of the time, but it's more flexible. If in case of elevated convection, you don't have to switch to a different parameter. And if it's a really tall or really short storm, you don't have to switch to something else because it tries to tell you the same thing. So what we're trying to do is come up with something that can combine all of these elements to tell you whether there's supercell potential, whether it's a short, tall, or elevated storm or standard surface-based, and to do it all consistently without you having to make some sort of decision prior to looking at it. Like, oh, well, because I think the storms will be elevated, I'm going to look at this different measure of vertical shear, which means you're already telling yourself the answer before you look at it. Okay, so we look at the effective bulk wind difference. We do the same sort of thing, same kind of plot, looking at the exact same groupings of storms we saw on the previous one. Turns out the effective bulk wind difference increases for all the supercell storms. It tends to be in the neighborhood of, this is plotted in meters per second, but you can convert that to knots, you get about 40 knots. And then on the far right, those are the marginal and non-supercell storms. So there's a big difference in the distributions. All the groups of supercells tend to be roughly 40 knots or greater, and the non-supercells fall well below that. Okay, so let's piece this together so that we can forecast storms that look like that, and hopefully you get to see them. I didn't see that one, except for that picture. Supercell composite. We want to combine the measures of CAPE and vertical shear that are relevant to supercell formation. And as I've mentioned, we've showed you what the climatological distributions look like. So we're going to normalize terms to those climatological distributions. And we use a nonlinear product of the normalized terms, which in a sense allows CAPE and shear to compensate for one another. If the low-level shear is relatively weak, it can be compensated for by large buoyancy and vice versa. And that's by multiplying the terms, you can get that effect. So when we look at the only term we haven't looked at so far would be the most unstable partial CAPE. The difference here is most of the supercells on the left tend to be above about 1,000. Now you notice most of the storms tend to be above about 1,000. That's a pretty common value. One thing that we're trying to do when you do a composite parameter like this, you don't want to have to first assume, well, given that there are supercells, this works. That's putting the cart before the horse, so to speak. So we have to consider the vast majority of the time when there is not 1,000 CAPE, like outside this evening. There's essentially no buoyancy. So we don't want it giving us false alarms in environments where there's no reason to be looking at it. So that's part of the reason CAPE, even though by itself is not a great discriminator between non-supercell and supercell thunderstorms, vertical shear is a much better discriminator, but CAPE is a very good discriminator between thunderstorm and non-thunderstorm environments. So a lot of its value is in that discrimination. Okay, so we end up with the effective layer supercell composite. And what we're doing is we're taking normalize the most unstable partial CAPE, and we pick the most unstable partial CAPE because we want it to work for elevated storms as well. We normalize to the effective bulk wind difference that is typical of supercells, and then we do the same thing with what's a sort of a low-end value for cyclonically rotating storms. And again, this is aiming at right-moving supercells. So we're just take the CAPE divided by 1,000 times the effective shear divided by 20 meters per second times the effective SRH divided by 50. The units all will cancel out in this case because we're dividing each one by itself. You end up with a non-dimensional parameter, and values roughly over 1 tend to favor cyclonic supercell environments. Okay, so when you apply this climatologically, same exact sample that we've been looking at. The vast majority of the supercells are here highlighted in the box. These are values well above about 2, and then the non-supercell storms tend to be collapsing down closer to 0. So the idea here is it does discriminate between the storm types, and in some sense, bigger supercell composite values are better. And how we demonstrate that is that we also have a big radar sample where we have the strength of the rotation with these storms, and indeed, on the right, circled in red, those are what we call strong mesocyclones. These are using, the differences in the inbound and outbounds anywhere within the lower to mid-troposphere or lower middle parts of the storm. The stronger rotating storms tend to have larger supercell composite values in the associated environments. So larger STP does tend to correspond to stronger mid-level rotation. So it bears out with actual radar data, whereas the weaker STP corresponds to weaker rotating storms. So there is some of the physical processes in there because the strength of the rotation of the storm is a direct indication of how strong is the supercell, because that's a reflection of the mesocyclone itself. Okay, weaknesses with this. One thing that's not explicitly considered is, and again, you can get this stuff from, I know people jump straight to the College of DuPage, Supercell Composite. They have a version of this. It's not the effective layer version. That doesn't tell you anything about whether you're going to get a thunderstorm or not, or a discrete storm. So you actually have to get discrete storms. That's a separate problem. The effective SRH estimate is sensitive to storm motion. We're assuming the bunker's storm motion. Now, as I note in the comment there, you're kind of putting the cart before the horse because you're assuming a supercell motion to try to forecast the supercell. But it's not necessarily all bad, because all we're trying to do is say, if we assume a typical right supercell motion for a cyclonic storm, how favorable is this profile for that type of storm motion? In a big curved hodograph, you're already going to have large SRH anyway. And in these straight hodographs, it'll be relatively smaller, and that right motion is important to get positive values of SRH down low. But they'll tend to be smaller than the big curved hodographs. Now, the strengths is this is a pretty simple way to estimate supercell potential based on the environment. I think more importantly, it gives you a wide range of environments you can look at: elevated storms, big tall ones, surface space, that sort of thing. And you don't have to change parameters. And there is a physical basis in the relevant processes. So it's not just completely made up and unrelated to what's happening. So we're trying to do something that looks like it reflects what we think are the relevant physical processes, and how can we convert that to some sort of parameter that we can calculate on a regular basis. So hopefully that makes sense, because if it doesn't, then the whole significant tornado parameter thing goes out the window, because we're doing the same kind of thing. We're trying to represent the relevant physical processes in terms of a composite parameter. Well, we're doing the same thing as SCP. Actually, if you look at the formulation for the significant tornado parameter, when you see it, it's got the SCP is kind of built into there, except we're just focusing on the elements that are also unique to tornadic right-moving storms. So we need some measure of vertical shear and buoyancy, and in this case, it helps to consider convective inhibition, because we're also interested in what's the resistance to the ascent down low. If there's a lot of convective inhibition in the background environment, then the resistance to ascent down low is large. And then we also need to consider, are these storms rooted at the ground, and is the vertical shear close to the ground so that the pressure perturbation is close to the ground, which gives us a stronger stretching term. And then finally, we have a term in there to estimate the potential for how cold will the downdrafts be, the rear RFD air. Okay, so we've looked at the same kind of, this is a little bit different sample of supercells. This one, I apologize, I was too lazy to get the QLCS tornado events that are on the left out of here. I think the ones on the right three boxes are discrete right-moving supercells. So the middle one is non-tornadic, weak tornadoes, and then F2 or greater tornadoes on the far right. So here, the tornado risk increases as the effective SRH increases, except you notice instead of very low values, it's in the order of 150 to 200 or greater. So it's when you start getting into the large values of effective SRH. So that's related to that pressure perturbation, so we're going to use that term to give us an estimate of how strong is the low-level stretching liable to be. ML Cape, we need buoyancy to get supercells. Since we are interested in surface-based storms, not elevated convection so much, and we want something with deep, strong updrafts, the 100 millibar mean layer parcel seems to be the best guess. Again, the supercells are all kind of lumped together. So we don't want to take some minimal value of buoyancy to normalize to. We're just going to take something that's typical of supercell environments. You notice in that case, the non-tornadic, weakly tornadic, and strong tornado producing storms all occupy similar parameter space. But the point is, they're all stronger than just background storms. It's larger cape than background storms. It's larger cape than the linear modes. So it is still important. And remember, we need buoyancy. So where does the buoyancy doesn't come from the downdraft, it's retaining the buoyancy of the inflow parcels. So if you start with a lot of buoyancy, it's easy to retain at least some of it. Okay, effective bulk wind difference, this is pretty straightforward. Most of the significant tornadic storms, they seem to be stronger across the board than just background supercells, so we consider that. And we also look at the LCL heights. Now in this case, higher is worse. High LCL implies low relative humidity. In this case, it's more of a limiting factor. It doesn't help you get tornadoes, but if the LCL heights get very high, that tends to make it more difficult. So we're penalizing for high LCL heights and no penalization as long as the LCL height's relatively low. So if the LCL height's about 1,000 meters, which is fairly low and is typical of significant tornado-producing supercells, it's when you transition from about 1,000 to 2,000 is where the penalization comes in. And we just don't have cases with the LCL height over 2,000 for significant supercell tornadoes. We also consider the inhibition. Again, same kind of idea where the inhibition gets larger. That's a negative. That impacts the low-level stretching potential. Most of the SIG-TOR storms are there with relatively weak convective inhibition. So when we piece it all together, this first part looks an awful lot like the supercell composite. It's just instead of most unstable parcel cape, we're making sure we route the buoyancy down near the ground. We have exactly the same effective bulk wind difference term in there. The helicity term is actually we normalize to a larger value because it's more important that we have strong rotation and a strong pressure perturbation close to the ground than it is just in the background supercell process. And then we just tack onto this an LCL term because higher is worse. You have to do some gymnastics here, so we subtract 1,000 from it, and this is essentially a way to represent penalizing it progressively as the LCL heights rise from 1,000 to 2,000. And then lastly, we throw the convective inhibition in, again, because the inhibition typically is negative, would be the units that come out, so we end up having to do an addition term. But the idea here is that as convective inhibition goes up over 200, tornadic supercells are really rare. As the LCL height goes up to about 2,000, they're rare. But low-level shear tends to get stronger. Buoyancy is modestly large, and it's clearly a supercell wind profile. All right, so when we slap in the same distributions, the ones on the left are non-tornadic supercells that produced either 2-inch or larger hail or significant wind gusts over hurricane force. So these are not trivial supercells. They produce significant severe, but they did not have tornadoes with them anywhere close to them in time and space. And you look on the far right, those are the violent tornado producers. You notice those are completely different parts of the parameter space. So the really high-end tornadoes tend to be in large STP environments, moist, strong shear, deep layer, strong low level, moderately large buoyancy, not much inhibition, and fairly moist. And that would be, again, you focus on the difference between these storms. The blue box is the non-tornadic ones. The red box is all the supercells that are right movers, and especially the significant tornado producers. And you notice the environments just get more interesting as the background damage ratings increase. So it does look like we are capturing something related to tornado formation, much like you saw SCP increased as rotational velocity in the storms increased. In this case, as tornado damage ratings increase, the background environment in terms of the STP also increases. So we've got some of the physical processes wrapped up in this. Does that mean we have it all figured out? Of course not. But at least there is some physical basis for doing it this way. All right, so again, the rationale, we want sustained supercell environments. You want to identify environments that favor strong low-level stretching. You want to have some way to estimate the resistance to the stretching. And again, when all these conditions are met, strong tornadoes are more probable, not guaranteed, but probable. And of course, there are weaknesses, just like the SCP. This doesn't say anything specific about storm initiation. or convective mode. And again, it is a pretty simplified estimate of the environment. We mentioned early on that an existing storm versus the formation of a storm, that's a different problem. So you got to be careful when you have mature storms moving into zones of very strong vertical shear but weaker buoyancy. And again, trying to characterize the rear flank downdraft characteristics with a single measure of moisture from the environment, it's a miracle that it works at all. But again, you should expect there to be some variability in how the LCL term responds. And again, we have no earthly way in operations to estimate vorticity generation in the RFD. You just can't do it. So there's always going to be some hand waving involved here. So just keep that in mind, that these tools are far from perfect, but the idea is you should be able to back away from them and explain how they're behaving the way they are. If you see STP of 10, you should be able to explain why. You should know, if you know the formulation, that the only way the values get that big, there has to be large CAPE or huge effective helicity. If the values are low, it could be because of any number of terms. And so you've got to look at the individual components, which is what pieces together the whole environment. So, the reason I go through this exercise of breaking down the composite parameters is because I want people to use them properly. They're not a panacea. But they do have some physical basis. It's not something that was pulled out of thin air with no correlation to the real world. There is a strong relationship to what's happening in the real world, but you have to know these weaknesses, and you have to consider all the weaknesses in the background environmental information that you're using to characterize this. You're going to calculate something like STP. There's a lot of moving parts in there. You're assuming a storm motion, you're assuming a wind profile, you've got a wind profile, you've got a moisture profile. All these things have to be accurate. Are the background numerical models that we use necessarily to fill in all the gaps out there, are they that accurate? I mean, the SPC mesoanalysis uses the RAP model. Is it perfect? No. So you're going to still have to look at observational data if you want to fill in the gaps, and especially if you want to find cases where these approaches or parameters are liable to fail. So again, I hope that you have a little better understanding of what goes into supercell formation, where you get sustained storms, rotation comes from, and what is the background source, as best we understand it now, for the rotation that leads to tornadogenesis. So hopefully that makes more sense. The session 5, which would be the one following this one, we sort of piece it together, no more conceptual models and all that. We're going to start using this information and start looking at real-world tornado outbreaks and how this information helps you identify them. So again, I appreciate everyone's attention, and that's all we've got for session 4. So thanks.